Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss a new topic regarding the loss of head due to obstruction in a pipe. So this is actually coming under the minor losses. As we have already discussed, the energy losses is of two types. One is major loss, another one is minor loss. So major loss is to happen due to the friction in the pipe. This is the major loss, and the minor loss used to happen. There are so many cases are there. By that, the minor loss is to consider. Okay, so this is because of friction, and this is because of few cases are there, like sudden expansion in the pipe, sudden contraction in the pipe, or exist from the pipe, entry in the pipe, or due to obstruction in the pipe also. So this is one of the reason of minor losses of energy. Okay, so let's discuss more about this. Suppose there is a pipe is there, and through this pipe the fluid is flowing with a velocity of v, and suddenly there is an obstruction. Okay, suddenly there is an obstruction came in the fluid flow. Okay, yeah. Now, due to this obstruction in the flow, you can see the fluid particles how it is flowing through it. Now see, in this part the fluid can move freely. Okay, and even after the section 2, if you consider, even after section 2, it will the fluid will be moved freely here. Okay, now due to this obstruction there is a reduction in velocity. Why this velocity reduction? That means there is a disturbance in velocity of this fluid. Why it happened? Because of this obstruction in the pipe. Okay, so here actually the fluid, how it will move due to obstruction, the fluid will move in this way. Okay, it's moving like this. Now similarly, the fluid will be change its path and it will move like this. Now you can see after it's moving, after it's completely moved, then it's came to a position, like it will come to a position, then again it is going to expand its path. Okay, so now the fluid may enlarge like this, in this way. Okay, all this fluid will be moved like this. Correct. So if you see, whenever there is an obstruction in the pipe, the loss of energy, as I told you, the loss of energy will takes place due to the reduction in area. Now see, previously how much area was there before the obstruction? What is the area of this pipe? Okay, and after the obstruction, even immediate, not after the immediate area obstruction of this area, let's take the area after the section 2. So here the area and this area, and what about this obstruction area? So there is a, or you can say there is a reduction in area. So reduction in area of what? The area of the cross section of the pipe. Due to this obstruction, the cross section of the pipe is reduced. Area of the pipe is reduced. Okay, where the obstruction is present, not the other places. Okay, so now you see how the fluid is moving. As I told you, like, it will come like this. So all this fluid will be change its path and it will be flows like this. Okay, so now due to this obstruction, the fluid was changed its path and it came to a point. So at this point, if you see, the fluid flow is having a minimum area. At this point, if I show you here, this is the point. Actually, I'll tell you, this is the CC point. I'll tell you what is CC. So at this point, the minimum area of this fluid flow occurs. So due to that, okay, this portion is called the vena contracta. This portion is called actually vena contracta. Okay, this vena contracta already you have discussed previously, and after this vena contracta, if you see, the fluid expands, or the fluid enlarges. Okay, so due to this conversion of this, reduction, then after that minimum area of this fluid flow occurs, and after that it enlarges. So due to this, there is some losses of energy will be identified, because due to that there is some vortex formation will be there in this, and the vortex will be given an impact on the fluid flow. So due to that, some losses will be happen in this. So this is actually mainly due to the enlargement in the enlargement of the area flow, you can say, of area of flow. So area flow of enlargement of what? Now, after the CC, after the obstruction, you can say, after the obstruction. So after the obstruction is what? And after the obstruction is CC or vena contracta. So where the loss of head takes place. Enlargement of area of flow. This is after, you can say, after the obstruction or after CC also, you can say. Okay. So here if you see, let's consider two different sections. So section 1, this is section 1 in the obstruction part, and section 2 actually after some distance of from the obstruction. So, and in middle, let obstruction, like, you know, there is a vena contracta formed here. So this is section CC. So let's find out what is the losses will be there, head loss due to the obstruction. So for that, let's consider, suppose this is the pipe. So let's consider A, which is the area of the pipe. Area of the pipe. So I just write in short form, area of pipe. And let's consider small a. Small a is the maximum, nothing but the maximum area of the obstruction, that we don't know how much area this obstruction is present. So you can write simply, you can write the area of obstruction. This is the area of obstruction. Okay. And next is here the velocity, V equal to what? We can write the velocity of the fluid or the liquid which is present in the pipe. Velocity of the fluid in the pipe. Okay, this is at the section 2. So what I can write here? Area and velocity. And here for this point also we have the area small a. At the section 2, similarly, if this is A1 and V1, similarly at section 2 also you can write area of the pipe at the section 2. So both will be similar here. Now we are considering both is similar. Why? Because I'll tell you. See here how much cross-sectional area is there at this point. No, actually this both cannot be same, because area of this section we are taking here. So before that, before obstruction, I can say this area, and after this area can be same, can be considered. So area at this point A2 is nothing but this A1 I have given. Yeah, area we can give this one, or else if you want to take, this is at the obstruction pipe, so no need, only you just can mention area of the pipe. So now here I can write A equal to A2. So this is not required, only one area can be considered, there is no issue in that. Okay, similarly at this point velocity will be also there. Okay, now at the CC point again we need to consider, at the CC point we can consider the area of the vena contracta, and VC the velocity at the velocity of the liquid at the vena contracta. So this is velocity of liquid at vena contracta, and this is area of liquid or area of fluid flow in the near to the vena contracta. Okay, so now the concept is actually here to find out this loss of head due to the obstruction. What we need to consider, actually this loss of, I can write here the loss of head due to the obstruction in the pipe can be written as actually the loss of head due to sudden expansion or sudden enlargement in the pipe. Okay, now sudden expansion which happened from which place to which place. Now if you see, sudden expansion need to be considered from this CC point, actually from the vena contracta to, you can say, up to section 2. So these things we need to identify. Now actually one more thing is there. Now this area A and small a we have taken. Now if I want to write A or the liquid which is flowing, okay, the liquid which is flowing from section 1, okay, through this, we can write the area of this, like apart from this area, like obstruction, what is the liquid is flowing through the pipe. So that is nothing but A minus A, because total area is A, capital A, area of the pipe, and the A small a is the area of the obstruction. So if I minus this one, like total area minus this a small area, so I can get this is a minus small capital A minus small a is nothing but area of flow of liquid or flow of fluid at section A, at section 1 we can write at this section what is the area of fluid flow. Okay, now this, as I told you, the loss of head due to obstruction is happening exactly due to the enlargement in the fluid flow. So this one already we have calculated previously. What is the head loss due to the expansion, or what is the HE? Now we know that HE equal to, we can write, we got there actually V1 minus V2 by 2G. This is whole square we got actually. So there there we have taken V1 and V2, like velocity at this section 1 and velocity at the section 2. But at this condition, if you see, it is not like that. We are not considering the section 1, because after crossing the section 1, again it came to a position where the area of this fluid flow is very less, and after that it expands. So we need to consider the section from CC. So the area of the flow, or you can say this one we can write in terms of nothing but, let me write in the next slide. So this one we can write HO, the head loss due to the obstruction. I can write this is VC on behalf of V1 and V2. Let me write this is VC and this is normal V. So VC minus V square by 2G. Okay, so this is the equation. Let's consider 1. Okay, now we know that exactly again to find out this VC or this value, let consider the continuity equation. We know that from the continuity equation we can write here AC VC. We know that A1 V1 equal to A2 V2. So by that concept we can write AC VC equal to here A V, area of the pipe, into velocity of the fluid in the pipe. So now AC equal to, we know that area of the cross section at the vena contracta. So what I'll write here, yeah, one more thing. Next is, let consider the CC. The CC is nothing but the coefficient of contraction. So coefficient of contraction, what is the ratio? Coefficient of contraction is nothing but the area of the vena contracta, area at the vena contracta, that is nothing but AC, area of the vena contracta, to the area of the fluid flow which is flowing through the pipe. So that means we can write through the pipe, we can consider this one A minus A. Which area we need to consider? Actually at this section, what is the area of the fluid is flowing. So that is A minus A. So this is the ratio of coefficient of contraction. Okay, so now what we can do here, we can put the value of this in this equation. That means from here we can find out what, now here we can find out AC equal to, we can write CC into A minus A. Correct. Now substitute the value. What is the value? Which value? AC value. AC is what? The area of vena contracta here. So put this value in this equation. So we can write, okay, here we can give a equation, suppose we can give a equation 2. So we can write here, put the value of AC in the equation 2. So we can write what? CC into A minus A into VC equal to A into V. Now again these things also we can write in terms of VC. As I told you here, VC is there. I want to identify the value of VC from this equation. So what I can write here, yeah, VC equal to AV divided by this total term. What is there? CC into A minus A, capital A minus small a. Now what we'll do is just put this, substitute the value of this VC in the equation 1. So we can write HC equal to, just put this value in this equation. Yeah, we need to write in bigger way. So and that means AV divided by CC A minus A minus V whole square and divided by divided by 2G. Now what I'll do here, if you see, yeah, CC A minus A. Now we can write this one in terms of, okay, 2G, let take it to outside, and here also V is there, now whole square is there, means this V, one V take common from here. This is one V, this is one V. So what I can write here, one V take common outside, like V will come means that V square will be there, suppose. Okay, V square, let take it common outside, and denominator 2G is there, so 2G, let take it outside. Now what we can write here again, what are the remaining things will be there, A by CC. So A by CC is nothing but A by CC into A minus A into A minus A. So this one we can give a square bracket. Okay, yeah, and here we can get V already gone, so one only single. So this is the square of this. Now finally what we got, now the head loss due to the obstruction in the pipe HC equal to, we got V square by 2G whole bracket capital A by CC A minus small a minus 1 bracket close square. So this is the final answer of the head loss due to the obstruction. Here we can go O actually. Here also we can give O, head loss due to the obstruction. Yeah, I hope you understand this concept. This is also similar kind of like, concept what is exactly due to the expansion or enlargement in the pipe. Okay, because from there only we have taken this equation, and just we identified some value here. That's it. If you're having any kind of query and doubt regarding this, you can give a comment on the comment box. Thank you.